have a lot in common, and so their needs are very similar, you would expect that at some level what they're doing matches what a similar business is doing, right? So a generic application architecture is an architecture for a software system that you can then configure and adapt to meet the specific needs of your client, right? So we use them as a starting point for architectural design. So we start off with something that generically fits the bill, and then we add in the specific details that make it suit your particular client. They can be used as a design checklist. So you can go, okay, here's my design, and there's the existing architectural pattern. Have I missed anything? Right? They can be used to organise the work of the development team, right? So splitting out the different sub-modules within the architectural design to different parts of the development team. You could decide that one part of the architectural design is exactly what you want, and so you look for other modules that have been already implemented to do that, that you can reuse. So you can say, okay, so this is a standard pattern, a standard application architecture. Other people have done it before. I wanted to do exactly the same thing. Can I use the software that they developed rather than developing it myself? And you can also use it as a vocabulary for talking about application types, right? So you might talk about the difference between a centralized system and a layered system, for example, to somebody who doesn't have a strong background in computing and doesn't understand what the implications would be in terms of the security and the reliability and the performance, right? So you can use them to illustrate particular points that you want to make. So we're going to look, again from the book, at two very widely used generic application architectures. Transaction processing systems, which include things like e-commerce systems and reservation systems, and language processing systems, which, as I said, compilers and command interpreters, language interpreters are examples of it. So first of all, transaction processing systems. So essentially, they process user requests for information from a database or requests to update the database. And from the user perspective, the transaction is a sequence of operations to satisfy a goal. So for example, your one particular transaction might be find the times of flights from London to Paris. Typically users use asynchronous requests for service, which are processed by a transaction manager. So an asynchronous request means that you're not waiting for a response, you're just going to take the response when you get it. Right? So you send off the query, and while that query is happening, you might be doing other things, waiting for it to come back to you. So here is a typical structure, right? So we have the I/O processing, so the user interface end of things. Then you have the application logic, the transaction manager, which is the thing that talks to the database. Okay, so here is where the user inputs their thing. There might be some sort of checks on the sanity of their input, you know, to make sure that they input a valid date, for example, if it's a date field, that type of thing, but it's very simple checking at that point. Then you have the application logic that takes the information that the user has input at their user interface level and transforms it into some sort of query, which then goes to the transaction manager, which then interrogates the database or changes the database if appropriate. Okay, so here is an ATM system. Right, most of you did a brilliant example of the diagram for an ATM system, or withdrawals from an ATM system. There were, a few sort of minor complications in some of them, but generally did that really well. But this is more generally about the different types of things that you can do with an ATM system, where you get the input at the cash machine. In the middle, you have the database, and then output from the database goes back to the cash machine, where it does whatever is the response to the transaction that's being happened. So it might be dispensing cash, it might be just returning the card. You'd expect it to be returning the card in most instances, except where they'd failed to input the PIN 3 times. Sometimes it swallows the card, but not all cash machines do. And printing the details. So that might be just if they just ask for an account balance, for example. You might be getting a receipt, that sort of thing. But it's a layered thing, so at a high level, we can look at it this way, but at a lower level of architectural design, you might have extra layers in between here, right? These two, in a sense, are both the user interface end. Okay, so it's a different representation of a layered architecture, if you like. An information systems architecture. So we have a generic architecture organized as a layered one. Transaction-based system, an interaction is generally involving database transactions. The layers include the user interface, the user communications, information retrieval, and the systems database. So this is what one layered architecture would look like in generic terms. Okay, so this is like your checklist. If you think that you've got this type of system, you would be wanting to make sure that you included at least these things, and possibly more. So in the textbook, they have this running example of the Mentacare system. So those of you who've been reading along in the textbook will be familiar with the Mentacare system. It's basically a medical dispensing medicine dispensing system, right? And so in this system, we have the web browser, the whole sort of data processing layer. Down here, you've got the bit that's interacting with the database, and at the bottom layer, you've got the database. Okay, so web-based information systems these days are almost always, you're talking about a browser-based system these days where the user interfaces are implemented using a web browser, sometimes with a separate app for your mobile device, but sometimes they just have a different form of the web page for your mobile device instead. So e-commerce systems are internet-based resource management systems. And in an e-commerce system, the application-specific layer includes additional functionality supporting a shopping cart. Right? And so the idea of the shopping cart is you have a series of transactions which put things into the shopping cart, and then a single transaction at the end to pay for the items in the shopping cart, rather than having to purchase each thing as a separate transaction. Let's get the next slide. Language processing systems. So, as I described earlier, the idea is that you accept either a natural language or an artificial language, like a computer language, as an input and generate some other representation of the language. So it might be that you're inputting the verbal audio form of the language and outputting text, It might be that you're taking text in one language and producing text in another language, or it might be that you're taking the representation of a computer program in a language and generating executable code. Okay, so they're all forms of the same thing. Sometimes, rather than generating executable code, as in the example of a language, you have what's known as an interpreter, which doesn't go the full step of generating the code, but just reinterprets it into another form. And so you would have something looking like this. So you have the source language input, and then you have a translator which checks the syntax, checks the semantics, and generates something. Then we have abstract machine code instructions. So this would be an example of something like Java, right? So Java doesn't produce code that is machine level code. It's abstract code that will run on any machine with a Java interpreter, right? So we have these abstract machine code instructions, which the interpreter then uses. It generally will take some data as input. Okay, so it might be user input, or it might be reading a file or something like that. And then for each of the instructions, it fetches the appropriate instruction, executes the instruction, and produces some results. Okay, so what that will work for any correctly formed program in the appropriate language. Okay, Java in the example I was talking about, but whatever one. So, given that representation, a compiler consists of, first of all, a lexical analyzer, which takes the input language tokens and converts them into an internal form. Now, the tokens are the subcomponent. So I think we'll work on it coming at 10:30 rather than 15:15 these days. Typically, think of them as words, right? The things between spaces. But it can be more than that, because in a programming language, you have things like an open bracket is a token and a closed bracket is a token. Right? A semicolon in most languages is a token. So the punctuation things are tokens as well as the words. We have a symbol table, which holds information about the names of things like the variables and the class names and that sort of thing. Okay, so the compiler makes use of those symbols. A syntax analyzer, which checks that, basically checks that the program has been written in a grammatically correct way, and if it isn't, at that point, rather than going through the rest of the program, it will say error on line 5, missing semicolon or whatever. After it has found that it's all syntactically correct, it generates what's known as a syntax tree, which is an internal structure that is closer to machine code than the original programming language was, but still not there. Then it has a semantic analyzer that uses information from the syntax tree to essentially check that the meaning is right. So you might have something that is grammatically correct, but you're trying to do things like assign a string to an integer variable. Okay? And that is semantically incorrect. So we have the semantic analyzer. Then, so basically, after that happens, you have another version of the syntax tree, or sometimes exactly the same, but it just says that it's correct. And from there, it generates the tree, from the tree generates the abstract machine code. Okay, so that's the way a compiler works. Now, that is the fastest thing I have ever done a description of a compiler. I used to spend a whole semester teaching about compilers, so don't worry if that was too difficult, right? each of those things was 1 or 2 weeks of my previous course on compilers. But the point is, it's a standard pattern. And it's a standard pattern not just for compilers. And what I used to say to my students who took this course was, most of you will not write compilers. Okay? But it's still valuable to learn about writing compilers because so many other things follow the same pattern. And language translation is the classic one. Okay? But not just language translation, a lot of music analysis follows the same pattern as well. So if you're going to do computational analysis of music, you're still, believe it or not, breaking it down into these sorts of patterns. You probably could use other techniques, sort of neural networks and machine learning techniques as well. They would do it a different way, but a classical method of music analysis would follow the same pattern as what I've described here, where you break the music down into blocks, generally defined by the beats within the music. You look at the changes in pitch and the changes in rhythm, which are the semantics and the syntax of the music, and that sort of thing. Right? So interesting that so many things follow the same pattern. So here is a repository architecture for a language processing system. And this is different perspective on the same system that we were looking at here in the previous one. So if I just... There. So there is one view of the architecture for a language processing system. And this is the process view. Okay, because we're talking about the way that things progress through the system. This one is another view of the architecture, but it's focusing on the perspective that you have a repository. And at the center of it all, in the repository, you've got the abstract syntax tree, the symbol table, the output definition, the grammar definition. All of those things are they're like the data that's involved with this thing. And then built around that, you've got the editor, something that's going to print out a nice representation of the tree for you, the lexical analysis, the different analyzers that you've got, the optimizer and the code generator. Okay, so these two we didn't talk about in the previous one because when you've got an interpreter, they're not there. But if you're doing a full compiler, the next stage after the semantic analysis is first to optimize the code and then to actually generate the low-level code for the machine. It's a different view of it again. Okay, so this is still conceptually the same thing, just different representations of the architecture that you could use to talk to different people about different aspects of the system. None of them are right, all of them are right, none of them are wrong, and none of them contradict each other either. They're just different views on the system. So this symbol table and syntax tree, they're used by all parts of the system except the lexical analysis hasn't yet generated the syntax tree. But there you've got your linear progression through the thing with this idea that you've got some data that's common to all parts of it. Okay, so point is, you have, even for the standard design patterns, different ways of thinking about the architecture. And depending on who you're talking to, one might be more appropriate than the other. Okay? If I was talking to my developers, this view would quite likely be a sensible thing because I'd say to them, look, you're all sharing this information, but I'm going to get each team to work on a different aspect here. Okay? And you need to be aware that you're all sharing this information, so don't go modifying it without telling anybody else because you'll affect their system as well. We need to agree on some common standards here, but beyond this boundary, you're not going to affect anyone else, the design changes that you make in here. Right? You could use this diagram to do a very similar thing. Okay? But it's talking about fewer components, right? So we didn't have the pretty print thing in this diagram here. The other one was a more fine-grained description of the system. Depending upon the size of your team, though, it might be appropriate to have it at this course level. If you're only going to have 4 sub-teams, you don't want to necessarily have 8 different things. So, you know, it just depends what you're talking about and who you're talking to. Okay, so in summary, just some recapping some definitions to start with. So a software architecture is a high-level description of how a software system is organised. And an architectural model can be used both to facilitate discussion about the best model to use for a system, and also to document the architecture of an existing or a proposed system. The architectural design decisions include decisions about the type of the application, the distribution of the system, both physically and logically, and the architectural styles to be used. Generally, you'll be trying to find a pattern that fits the system that you want, rather than trying to do it from complete scratch. You can document them from several different perspectives, such as a conceptual view, a logical view, a process view, or a development view. And that architectural pattern is that stylized abstract description of good practice. Okay? And basically people have been doing this type of thing for so long now that there are accepted patterns of use. So you should be just using the text essentially. As I said, Somerville has a good summary of a whole bunch of architectural patterns, but any textbook, good textbook on software engineering should do. Okay, have you got any questions before we go to the discussion? Please, if when you review the lecture you have questions, just email me, okay? I know several of you have been recording the lecture, and that's absolutely fine. I encourage you to share your recordings so that everybody has access if they want it. If you have further questions, please ask me. All right? Okay, so first of all, explain why design conflicts might arise when designing an architecture for both availability and security being the most important. So if we want the system to be available, high availability, what do we need to ensure?
If we want it to be available, we need to ensure that everyone can access it.
Yep. And how do we ensure that everyone can access it? The interface? Yeah, no, more than that.
Make it available, for example, by access through a browser, or by their mobile.
Yeah. So if they go to access it via their browser, and, well, what happens if they can't? Why might they not be able to access it via their browser?
Because maybe sometimes they have only their mobile,
Yeah.
and it is easier for them to use their mobile instead of go home and then open their system.
Okay, but say there was an interface that allowed you to access it via your mobile. In what instance would they not be able to use that interface?
Well, they might not be able to use it because we create some security requirements that forbids them from entering some parts of the system.
No, I think you're all missing the obvious one, which is if, say I wanted to access MOL, and this happened last night when all the staff were trying to upload their project descriptions for you to choose from in a week or so. MOL crashed and people were just getting an error.
Maybe because multiple user access the same system in the same time. This is make overloading or something.
Yeah, so this is the type of thing that happens, but it could just be that the computer crashed, okay? So if we want it to have high availability, we need to make sure that it isn't a single point of failure. We need to have multiple copies of it so that people are automatically redirected to an alternative when one of the servers is not serving it, whether it's because of a localized network problem, or there's computer crashes, or there are too many people trying to access, whatever reason, there need to be multiple copies, right? But security conflicts with that. Why?
Because if we have multiple copies, maybe sometimes
The more copies you have of the data, the more difficult it is to keep it secure. Okay, the more points there are for people to attack it and get access to it. So these two things are quite conflicting in their requirements. And if they were both had extremely high priority, it would be a very difficult problem to solve. Okay? And you would have to probably make compromises somewhere. But the question is, which one are you going to compromise? Are you going to compromise availability, or are you going to compromise security? Or maybe it just means that the security measures that you have to put in place are even more intense on the multiple different copies of the data, something like that. But it does add extra complexity to the architectural design. Okay, so this next one, given the time, I'm going to ask you to do in your own time rather than discuss today, which is to use the basic model of an information system presented in 6.18, which is the same as what's here, to suggest the components that might be part of an app for a mobile device that displays information about flights arriving and departing from a particular airport. Right? Now, it's not all going to be on the mobile device, okay? Something like this is going to have to be a client-server type architecture underneath it all. So which parts are going to be on the mobile device and which parts are going to be on the server? I want you to include that in your answer to the question. Okay, so what fundamental questions should be addressed in architectural design? So if you are starting out the architectural design of your system, what do you need to include in the architectural design? What are the basic things? Or before you start, what do you need to consider?
I think the first one is the stakeholders' needs.
The stakeholders' needs, yes. So who is going to be affected by this, and how is that going to influence your architectural design? That's good. What else?
Interface.
You are going to have an interface, but the design of your interface isn't going to be part of your... so you will have an interface layer, but that's probably all you have in your architectural design. You don't have any details about it. That will come in the later stage of design process. Okay?
I think it's important to take care of the availability of hardware.
Yep.
And also if if there is any existing system, we should take care about this one.
Yep, they're both good points. So what hardware are you going to be using, and how is your system going to be distributed over that hardware, right? And are there any legacy systems, so existing systems that you need to integrate with or communicate with that are going to affect the design of your system. Probably the first question you should ask is there a generic pattern that you can use? Does your proposed system match with one of these existing architectural patterns that we've been talking about? Okay, because that will focus the development of your architectural design. You have a template to start on and you just fill in the details. Okay, and the last question. What's the most important advantage of a client-server architecture? We haven't discussed this today. Something for you to think about.
Isolated architecture. Every component is isolated.
Yeah, so that's essentially it. So if you've got most of your processing happening on one server, and then you've got a whole lot of clients,
Yeah.
you can change your server without affecting all of the clients. I mean, there might be a little bit of downtime while you switch over to your new server, but it's there separate, and you can just focus on that one thing, right? Is that what you were meaning?
What I mean is because this is isolated architecture, so it may helpful for change the whole architecture of the system.
Yeah, so you have, if you want to change your system,
Yeah.
because most of the processor is done on that one server, or maybe multiple servers, but you can change a server without affecting the rest of the system. It is self-contained and isolated, right? So it's very easy. Rather than a distributed system where you have lots of different components that talk to each other, you change one, it's going to affect the information flow around the system. When you're changing a server, you are going to have downtime unless you can do a hot swap. Does everybody understand what I mean by a hot swap? Okay, so a hot swap, say I had a server running on this computer here, and I've got a whole lot of clients talking to it. I'm going to run a new server and I'm going to put it on a new machine. And so I start it up before I shut this one down. And then when I shut this one down, I basically send a message that redirects all of the clients to the new one. So they have a momentary glitch where they switch over to the new server, but it is just that time that it takes the time to change the address. So it's a hot swap because this one is already running hot when this one turns off. Okay? An alternative method would be, I'm going to do it on the same machine, in which case I would need to shut down the existing server, restart with the new one, and then there'll be a slight delay in between when the clients lose connection to the old server and get connection to the new one that starts up. Okay? But you want to minimize to the client the time that the service is unavailable. Okay? What you really don't want to do is to shut down the old server, try to start the new one and discover that it's not working. Okay? It happens a disturbing amount of time. Okay, there was a very bad case of it with the internet banking with one of the British banks, I can't remember, at Easter last year. And the entire bank's customers lost their internet banking for 4 days over at Easter because they started a new internet banking server and there was something wrong and it took them that long to fix it. Okay, because they hadn't done proper testing. Very bad software project management. You know, for something like that, which is just mission critical, you have to have everything perfect before it goes live. Okay, so that's all.